Okay, so welcome everyone to our seminar this week. Thank you for coming along. It's nice to see we've got a good mix of students and staff, so it's great. Thank you for coming. And it's my pleasure to welcome Sam Broom-Fendley, who is currently in Cornwall. I'm sorry we can't actually be physically welcoming you to Portsmouth, hopefully at some other time. But it's great to get to hear about your research today. So I think Sam is going to sort of introduce himself in his talk, but I'll just briefly do a quick intro. So Sam did his BSc at UCL and then went on to do an MRes in geochemistry at Royal Holloway. And after that, he moved over to Camborne School of Mines, where he's been ever since. So working on PhD and postdoc, working on mostly rare earth element deposits that he's going to be telling us about today. So thank you very much, Sam, and looking forward to the talk.
Okay, thanks very much, Catherine. And in these modern times, welcome to my house. And thank you all for simultaneously inviting me into your houses so I can give this talk to you. Today, I'm going to sort of tell you about how we make a rare earth carbonatite. So I want to put your imagination hats on and pretend that we are gods of this earth and we are creating it and adding the right ingredients to make a rare earth rich carbonatite. And I'll tell you what I mean by rare earths and carbonatites in just a moment. But I thought before we got started, because I'm not there to have that nice chit chat with you beforehand, I thought I'd give you a brief summary of who I am. I'm a NERC funded research fellow based at Camborne School of Mines and part of the rare earth and carbonatite group that we have here, led by Francis Wall, with a diverse range of co-stars and co-hosts as well. So I have a broad interest in sort of mineral deposit geology, but as Catherine mentioned, I've spent the last 10 years focusing on carbonatite hosted deposits. And in my day-to-day research, I use field observations, mineralogy and geochemistry, not so much field observations over the last couple of years, but mineralogy and geochemistry to understand the where, when, and how of rare earth mineralization. And I've worked mostly with companies in Southern Africa, and I've also have a spin-out company myself, which is exploring for rare earths in Namibia and in the process of floating on the Toronto Stock Exchange at the moment. Exciting. So I mentioned the rare earths. We may be familiar with the rare earths from a geochemical background, and many of us probably will have heard of them by now. But just to introduce ourselves again, what are they? They are the lanthanide group of the periodic table here, plus yttrium, and some people also include scandium. And in geology, these are of interest to us because they all have broadly the same 3+ charge, but differing ionic radius throughout the group. So we can use them to track petrogenetic processes, particularly in igneous petrology. And it's a bit of a cliche that the rare earths are rare. They're indeed not that rare in the crust, but they're quite broadly distributed so that they don't form particularly large economic deposits by themselves. They're often distributed throughout the crust. And we can make a comparison here with copper. Concentrations at about 66 ppm in the crust. Rare earths are not much lower than that. So the rare earths are of economic interest because of their use in what are called neodymium iron boron magnets. These are high strength permanent magnets that are used in electric vehicles, in the drivetrain of electric vehicles, and in the turbines for wind energy. And we have very ambitious green energy targets in the UK to move completely towards battery electric vehicles from 2030 for all new car sales, but also to power all UK homes by wind turbines come 2030 as well. And so the effect of these targets and of the recent growth in renewable energy technologies means that there's an ever increasing demand for neodymium iron boron magnets, which can't be substituted in these techs. And so with this increase in demand for magnets, we also see an increase in demand, of course, for the rare earths, particularly neodymium, which is used in the neodymium iron boron magnets, but also samarium, which is used in samarium cobalt magnets, which are less strong, as well as praseodymium, dysprosium, and terbium, which are all needed to stabilize magnets at different temperatures. So if we want to go from this sort of geological exploration scene where we go out to site and drill holes and drive out in our Hiluxes and use diesel generators, to this more sort of pastoral scene where we're using wind turbines to power our exploration efforts, and we're all whizzing around in our nice shiny red Teslas, then we need to extract up to 100 to 200 grams of rare earths per megawatt in our wind turbine, and some of the largest wind turbines that we can get are 14 megawatts currently, and up to 2.5 kilos per Tesla that is put out to use in the drive magnets which propel the vehicles forward. And where do we get these rare earths from? Well, we get them from carbonatites. Carbonatites, for those of you who are unfamiliar, these are igneous rocks which have more than 50% carbonate minerals, and the sort of classic textbook one, which is the only currently active carbonatite volcano on Earth at the moment, is here. This is Old Donyo Lengai in Tanzania. It's quite spectacular. This isn't my photo, this is one ripped from the internet, I'm afraid. But it's quite a spectacular site where you have these natrocarbonatite flows, which are composed of sodium, potassium, and carbonate minerals, which have the lowest temperature of any lava on Earth, reaching down to 600 degrees. Most carbonatites, though, most carbonatites historically, though, are intrusive bodies, and these are bodies which have exceptional potential to form a mineral deposit. So if you're wandering around in the bush and you should happen across a carbonatite in these unstamped lands, you have a higher chance than almost any other rock type of it being a mineral deposit. So to give you some numbers, 6% of the known 500 or so carbonatites host mines where some sort of commodity is extracted. 3% of those host mines which are now closed, and 11% contain an established mineral resource. So people have done the work and determined that there's enough material there to extract it. Most famously, these are deposits, these are rock types which host the rare earths, but the carbonatites also host large quantities of phosphorus, niobium, zirconium, iron, perhaps less glamorous, and fluorine, and probably least glamorous of all is the fact that they're made of carbonate and are used for limestones and cements. But as I mentioned, carbonatites are best known for their very large, high-grade rare earth deposits. So if we look at a comparison of different rare earth deposit types, those that are related to carbonatites, alkali silicate rocks, and this other type called ion absorption deposits, which I'm not going to go into, and we can compare their size. So this is the tonnage of rare earths contained within them in the blue bars, and their grade. So this is the percentage rare earth per ton. You can see that carbonatite related, they have some of the largest deposits, similar to alkali related deposits, but have grades in these red crosses reaching upwards of around 8% rare earth oxides. These are very high grade deposits, and they're also rich in the rare earths which are needed to make batteries, such as neodymium. But this is not universally true. Not all carbonatites, are rare earth rich. It's been famously said by a colleague in Canada that there are carbonatites and carbonatites and carbonatites. And so today what I want to do is go through with you the processes of what we need to do to make a rare earth rich carbonatite. We've got a 5-step plan for success, combining these different factors: a geodynamic environment, the right geodynamic environment, going through the processes of mineral fractionation, making a brine melt, hydrothermally altering it, and then weathering the deposit down. And so the rest of the talk is a shameless plug of this paper that myself and my co-authors, Michael Annenberg and Wei Chen, have written and is just come back from review in Elements, is out in October this year. So if you switch off and find that this talk is glazing over, then you can always pick up the paper later in the year and read up on what I've said. Okay, so we're going to go through each of these steps now to make our perfect carbonatite. So the first step is the sort of background geodynamic environment where we need to combine all of the aspects of our ingredients for our rare earth deposit and bring them together to the surface. So by way of a point, almost all carbonatites originate from a metasomatized mantle being a mantle source which has been metasomatized in some way by fluids derived either from a subducted plate, that could be a modern plate subduction environment, or more commonly an ancient subduction environment, which is devolatilized and moved, most importantly, carbon, and for this talk, importantly, rare earths from the slab into the metasomatized mantle wedge, as well as other elements as fluxes. There are those as well from isotopic data who invoke a plume component as well. And one of the key points that we've sort of gone through as part of this paper is that actually, whichever way you've metasomatized your mantle, it doesn't really matter whether it's from a plume, subduction, or some sort of miraculous fertilization event, because you just need a mantle with the rare earths and carbon dioxide in it to make a carbonatite melt, no matter what the isotopic source is. And there's a key point as well here. The fertilization of the mantle does not have to immediately precede carbonatite magnetism. In fact, it can happen many millions or even billions of years before that carbonatite reaches the surface and forms an intrusion. But you have to get it to the surface somehow, and to do this, we need deep crustal fractures penetrating through that crust to release the melt from the mantle. And these are either formed during an intracontinental rifting, so continental rifting event, or less commonly during post-collisional extension, so in the extension that follows a orogenic event. And I'm not going to talk so much about post-collisional carbonatites today. They're a bit of a funky, weird one. There are some who consider them to be more fertile, so more likely to form a rare earth deposit, but this is based on a limited number of studies at the moment. Instead, I'm going to focus on rifting in an intracontinental environment. This is the more classic sort of East African rift tectonic setting. And the key point here is that we've set our geodynamic environment. We've metasomatized the mantle. We've got that melt to the surface. And at this point, our whole rare earth budget for all of the next steps that we're going to go through is set. We have a fixed amount of rare earths. So every step after this is effectively going to be about somehow removing the non-rare earthy stuff from our melt, then fluid, then weathering environment. Okay, there's no addition of rare earths from somewhere else into our system. Okay, so we need a metasomatized mantle, a means to get that melt to the surface. Let's take a look now at igneous processes, mineral fractionation. But before I do that, I just want to have a brief note about liquid admissibility to get this out of the way. Carbonatite melts can form from two different sources. We can either have direct melting of a carbonated mantle and forming a carbonate melt straight away, which ascends to the surface, or we can have an evolved carbonated alkaline silicate melt, which then undergoes admissibility or fractionation to generate a separate carbonatite melt. So you can either have carbonatite melt going to the surface by itself or evolving from an alkaline silicate source. And this separation event is termed liquid admissibility. And when I say liquid admissibility, this is the unmixing of two liquids which are no longer soluble within each other. And a classic example here is oil and water. And we know that liquid admissibility does occur in carbonatites. We have experimental evidence which proves that it can. And we have melt inclusions, like this example from Kerry Macy in Tanzania, where we have a silicate melt, a carbonate melt, and a fluid bubble all contained within one small melt inclusion. So this is live evidence of immiscibility happening, the different melts separating out into different globules. Okay. So this process of immiscibility, we know from experimental studies, can lead to the rare earths partitioning into the carbonatite melt. So partitioning means the rare earths are going into the carbonatite melt over the silicate melt. But this, how much they partition, very much depends on the composition and conditions of the silicate melt when immiscibility happens, when you exsolve your carbonatite. So there are some conditions where the exsolved carbonatite melt can have very little in the way of rare earths, especially if it's exsolved from a poorly evolved silicate rock, silicate melt. So some experimental work from a group in France led by Zineb Nabil has shown this quite recently, where the more fractionated your carbonated silicate melt is, so this is calcium oxide in the melt along the bottom here. So the lower the calcium oxide content, the more fractionated it is, the higher the partition coefficient of the rare earths into the carbonatite melt is. So this is D of lanthanum from the carbonatite melt of the silicate melt here. So the higher partition coefficients for much more evolved melts. And an evolved melt in the alkaline, carbonated alkaline silicate system is something of a sort of phonolytic composition. This is all well and good. So immiscibility does happen and it is important, but it might not happen in all carbonatites. So 24% of all carbonatites on Earth have no associated alkaline igneous silicate rocks. And this all includes some of the highest rare earth grade carbonatites. So this is one that I work on here, mapped in Malawi. This is the Kangenkundi carbonatite, and it's just composed of different carbonatite stages and then brecciated host silicate rocks. And one of the things that this shows to me is that no matter what the process of immiscibility is, the process of the evolution of our carbonatite melt is as if not more important than the behavior of the alkaline silicate melt beforehand. Okay, so from now on, we're going to be exploring fractionation of a pure carbonatite melt in isolation and not considering the silicate melt, although some of these phases could fractionate beforehand. So when we're considering mineral fractionation in a carbonatite, we need to be aware that there are different flavors of carbonatite. It's not a single rock type, but it's spectrum in the same way that's for basalts and granites, silicate rocks. We're talking about carbonate rocks here. So we evolve through a different spectrum of compositions. The most common and most abundant is calcite carbonatite. This is understandably where the bulk carbonate mineral is calcite, and we go through a dolomite composition to a ferrocarbonatite composition where our dominant carbonate mineral is either anchorite or siderite, the magnesium and iron carbonates. Okay, so if we look at this on a trigonal plot with calcium oxide or calcium carbonate at the top, magnesium carbonate in this bottom corner, and iron carbonate here, we evolve from here, the calcium carbonate corner, down to a dolomite composition, then across and down to a ferrocarbonatite. And a key point I should make here as well is that these different rocks are not representative of the melt composition. Okay, this is representative of what has crystallized at that time. And we lose in a carbonatite a lot of volatile components from the system. And I'll touch on that briefly in a moment. But most importantly is not representative here is the sodium and potassium content of a carbonatite melt. So just to give you a brief flavor of the minerals, as well as calcite, dolomite, and iron carbonates, we have minerals such as magnetite, biotite, apatite occurring in our carbonatites. And this trend from calcite carbonatite to dolomite carbonatite to iron-rich carbonatite is borne out in most complexes in the structures that we see. So this is a classic example here of Chilwa Island in Malawi, which was the first carbonatite to be discovered and identified in Africa. And it's also quite a textbook example where we have calcite carbonatite forming the first phase around the outside, and then cross-cut by dolomite carbonatite in this sort of pinkish color, and then with a central core of ferrocarbonatite here in the middle. And I mentioned that these are not representative of the sodium and potassium contents of the carbonatites, and that's because those elements partition out of the melt itself and react with the surrounding country rock, creating this rock type called phenite, which is a metasomatized country rock with elevated sodium and potassium concentrations. So as we progress from calcite, dolomite to iron carbonatites, we reach into the center of our carbonatite, we not only increase the iron and manganese contents of our rock, but we also increase our rare earth content. So this is an example of some data from a carbonatite I've worked on, the Songwe Hill carbonatite in Malawi. We see rare earths, total rare earth oxide concentration, so rare earths along the bottom against manganese and iron, where you can see that the more anchoritic carbonatites are more rare earth rich. And with this as well comes an increase in strontium and barium. So we can broadly consider this to be a fractionation series, even though we don't have rock compositions which are completely representative of the melt. But we know from both experimental work and from these field relationships that we are removing minerals from our evolving carbonatite melt. So I've listed here on the bottom left side the various minerals that we can fractionate in a evolving carbonatite series. And most of these have a low uptake of the rare earth elements. They structurally do not incorporate much in the way of rare earths or are not particularly significant in a carbonatite. The exception here is apatite, and this is a key point. We need to control the behavior of apatite because apatite can remove rare earths from our system. So a brief reminder to those of you who are thinking apatite, I can't quite remember what that is. This is a calcium phosphate, and in this case I'm talking about fluorapatite, which is the fluorine end member calcium phosphate. For the most part, your teeth are made of apatite, hydroxyl apatite. Apatite is ubiquitous in carbonatites. It occurs in almost every single carbonatite on Earth. And it's a very early phase. It forms one of the first crystalline products to form in a cooling carbonatite. And it forms cumulate rocks along with magnetite, pyrochlore, and other phases. And this is particularly advantageous in some cases. This is the Kordore mine in Russia, which is an apatite and iron ore mine. But it's disadvantageous because the rare earths can substitute into apatite and be removed from our evolving carbonatite melt. So rare earths can enter the apatite structure as a coupled substitution with either sodium or silicon through swapping into the calcium and phosphate sites. And this is a problem because if we remove rare earths from our evolving carbonatite melt, we can sterilize the deposit and our carbonatite will not form a nice rare earth deposit. So we need to either suppress crystallization of apatite, which is challenging because apatite forms in almost all rare earth deposits. There's a high phosphorus content. Or we need to suppress the uptake of rare earths in apatite. And how do we do this? Well, we suppress the activity of silicon in our carbonatite melt. So why silicon and why not sodium? Well, we don't entirely know why, or at least I don't entirely know why, but sodium doesn't partition, despite having a high sodium content in our early carbonatite melts, sodium doesn't seem to partition into high temperature apatite in a carbonatite. Sodium-rich apatite only occurs relatively late in the evolution of a carbonatite. And instead, the rare earth incorporation in apatite is controlled entirely by silicon. So silicon activities in carbonatite systems are typically not particularly high because the bulk of the melt is carbonatite, carbonate, of course. But we can have some silicicarbonatites, so carbonatites with some silica content. And we can also have input and increase of silica activities due to wall rock assimilation. So rather than focus on this sort of small diagram here, I thought we'd look at this diagram and visualize what's happening so far in our fractionation series. So let's just take a moment to take this diagram in. From left to right here, this is a schematic model of an ascending and fractionating carbonatite melt, crystallizing calcite, dolomite, magnetite, apatite, and silicate minerals. Along the bottom here, we have an alkali-rich carbonatite, so we're one with a low silica activity. And at the top here, we have a silica-rich carbonatite, either from having an initial higher silicon concentration or through wall rock assimilation. We've got a nice bit of country rock here where silicon can come into our carbonatite melt. And in this top scenario, and I just want to focus on this first part of diagrams so far in the talk, we can see that our silicon activity is high. So as our minerals are crystallized out of our evolving melt, we partition rare earths with silicon into crystallizing apatite and effectively sterilize our deposit. Whereas in our alkali-rich carbonatite, we progress with a low silicon activity and retain rare earths along with other phases in our residual melt. And we'll come back to this diagram later in the talk and explore the right-hand side about the final effects. So we've got our metasomatized mantle and we've got it a melt to the surface. And to progress on our journey of forming a rare earth deposit, we've fractionated out much of the stuff which isn't rare earths, and we've managed to suppress silicon activity such that we haven't lost rare earths through the crystallization of apatite. Before I go into this brine melt stage here, what I want to do is just sort of touch briefly on a problem of the term hydrothermal fluids when we're dealing with alkaline and rocks and carbonatites. And when we talk about hydrothermal fluids and we're thinking about sort of normal rocks such as a basalt, we have crystallization of, say, plagioclase and pyroxene and nice normal minerals to a point, and then you have a hiatus where magmatic processes effectively cease, and then hydrothermal processes come in and cross-cut, forming along brittle deformation, etc., and you get your secondary recrystallization, etc. In alkaline rocks and carbonatites, there's very much more a blurred line between magmatic processes and hydrothermal processes. And with magmatic processes continuing down to much lower temperatures than we would consider normal in a sort of basaltic system. And we can see this in this next stage that has been conjured up quite recently or described quite recently, which is the brine melt stage. Because as we are having our carbonatite evolve and fractionate out carbonate minerals, it's getting to the point where it's no longer really a carbonatite melt at all. And if we look at some melt inclusion work from Prokopiev and others in 2016, who came up with this brine melt term, we can see actually the residual melt fluid is very much a mixture of anhydrite, sylvite, so potassium chloride, halite, sodium chloride, a little bit of CO2, a little bit of water, and some remaining carbonate minerals. Okay, it's not really a carbonatite melt anymore. And what happens is that the low water content of these remaining phases and the composition of these remaining phases act as a flux to keep the solidus low. And so this fluid sort of behaves as this transition phase between a melt and a fluid, which is quite difficult to describe, but it's termed the brine melt stage. And it's this stage which is really important for rare earth mineralization, and probably the most important stage for forming a rare earth deposit in general. And if all is well and you reach this brine melt stage without losing your rare earths, then the rare earths are typically sufficiently enriched to start forming early rare earth minerals. So here we have some melt inclusions again, and we have ansolite, which is a rare earth carbonate starting to crystallize. So if we returned this schematic diagram, we can see that our ascending and fractionating carbonatite melt is removing calcium, magnesium, iron, and phosphorus, and the residual phase, this bright green brine melt phase here, contains elements such as sodium, potassium, sulfur, chlorine, and fluorine, and strontium, which are, as well as the rare earths. And it's at this stage that we start to sequester our rare earths in these alkali rare earth carbonates. So alkali could be the sodium or potassium, but generally sodium, rare earth, as well as strontium and barium carbonates, such as bourbonkite. Bourbonkite being the most important rare earth mineral that I suspect you've never heard of. Okay, so bourbonkite, which I'm going to be talking a lot about in the rest of this talk, is a sodium, calcium, strontium, barium, rare earth carbonate. And it's extremely rare, it's extremely ephemeral, but it's one of the first minerals to form in an evolving rare earth rich carbonatite. And it occurs in interstices between carbonate minerals, as well as in some awesome late pegmatites. So this is an example from Khibiny in Russia, where we have these nice hexagonal bourbonkite form. And we can see a part of the pegmatite here. And also these awesome pegmatites. This is from Wigu Hill in Tanzania, where we get these large euhedral hexagonal crystals exhibiting this extraordinary unidirectional crystallization temperatures as all these pegmatites form from the outside in a rapid crystallization. Okay. So by this point, if we're crystallizing bourbonkite or an alkali rare earth carbonate from our carbonatite melt, then we've actually probably done enough to make a viable rare earth ore deposit. And everything we do from here on in is either going to make things worse or at least a little bit more difficult and confusing, in my opinion. So the most important stages, arguably, are the fractionation and formation of a brine melt. Because after this point, we're looking at hydrothermal alteration. Those last remaining carbonic and hydrous components in our carbonatite brine melt residual phase start to exsolve and boil. And this can happen in carbonatites possibly many, many times. And this leads to fracturing and of the surrounding country rock. This is in the background is an example from the Songwei Hills. This is my colleague Paul, which is completely destroyed the surrounding phenite in this case, so the host metasomatized country rock, as well as the carbonatite itself is just a breccia pipe now. And this fracturing and brecciation leads to the incorporation of meteoric water, so surrounding pore waters, into the evolving carbonatite-derived fluid. And this incorporation of surrounding meteoric water has a pretty profound effect on rare earth mineralization, and generally speaking, goes and messes everything up. One of the first things we see is that our beautiful hexagonal bourbonkite crystals start to be replaced. So bourbonkite is a highly soluble phase. It dissolves in water relatively easily. And where we have water ingress, which is in almost all carbonatites, we see bourbonkite being replaced, sometimes partially, but usually wholly, by an assemblage of rare earth fluorine carbonates, strontianite, and barite. So these are the components which make up bourbonkite, separating out into individual, less soluble phases. And we see this retained in hexagonal pseudomorphs and partially completed, like here, in this case in Shashuangdong in China, where our residual bourbonkite is slowly being replaced by this assemblage of rare earth fluorocarbonates. And I lied to you earlier, these aren't actually bourbonkite crystals, but are in fact pseudomorphs of bourbonkite. So these are all look like bourbonkite on a hand specimen scale, but when you cut a section of them and you look at the nice hexagon, you can see that this has been replaced in this case by strontianite, monozyte, bastnasite, and not shown in this photo, but also barite. So when we have an influx of meteoric water into our rock, our Bourbonkite mineral is being replaced by this assemblage of rare earth fluorocarbonates and other phases. Okay. And in fact, often the only evidence that Bourbonkite was ever there are these pseudomorphs. The preservation of Bourbonkite is extremely rare. And these pseudomorphs, while more common than preserved Bourbonkite, are also very rare. And more often than not, what we actually see is an assemblage that looks a bit like this, where we have little stringers of rare earth minerals and the same assemblage, so rare earth fluorocarbonates, strontianite and barite, but in these stringers or vug-like accumulations. And this is an example from Songway Hill. And most or many authors, based on some experimental work done sort of last decade, interpret this rare earth mineralization in vugs and stringers as a direct precipitation of the rare earth phases from an acidic hydrothermal fluid. So they imagine that you have an evolved carbonatite. We have this jump from a magmatic system to a hydrothermal system, and then we have an acidic fluid precipitating rare earth minerals. And experimentally, this works reasonably well, but there's a bit of a challenge here because we're essentially evolving an acidic fluid from a very alkaline precursor, which is an unlikely scenario, and anything is going to back react almost immediately. And we also know from recent experimental work that Michael, the co-author on this talk and paper, has done, that the formation of these rare earth fluorocarbonates from an evolving alkaline rock and the direct precipitation of them is likely to be very rare and very difficult to do. So the proposal that we have in this paper and the sort of central idea behind this talk is that instead of direct precipitation of rare earth minerals from hydrothermal fluid in a carbonatite, what we're actually seeing is water ingress replacing alkali rare earth carbonates in all cases. One of the difficulties behind this is that the Bourbonkite is almost always replaced, but recent work that I've got, which is in prep for publication now, is the preservation in these assemblages of rare earth fluorocarbonates of very small Bourbonkite mineral inclusions, such as is shown here. This is preserved in barite with a rare earth fluorocarbonate synthesite and strontianite around the outside. We have these small inclusions of Bourbonkite. So this is some indication that there's a Bourbonkite or alkali rare earth precursor. And so that's one of the main points that I want to really get across in this talk, is this idea that hydrous fluids don't directly precipitate rare earth minerals, but they recrystallize the soluble sodium rare earth carbonates into something that is less soluble. Hydrothermal fluids, though, can have a profound effect on all minerals in a carbonatite, and most minerals in a carbonatite have been broken down to some degree by some hydrothermal phases. And when you look at sort of a wild carbonatite, actually it's a bit of a dog's dinner and everything's partially dissolved, and it's really difficult to reconstruct back to these magmatic processes. So in the case here, this is work that colleague Delia Cangelosi undertook at Leeds. She looked at the Okurusu carbonatite and demonstrated that here in the Okurusu carbonatite, we see breakdown of primary phases, in this case calcite, but also apatite, which, as we know, can incorporate a small amount of rare earth during earlier igneous steps. Then they break down in a hydrothermal fluid passes through, and we can see that here, and recrystallize, and we form little strontianite grains, recrystallize calcite, and here, very small amounts of reformed rare earth minerals. So rather than this Bourbonkite route, it is also possible to form rare earth minerals in a carbonatite through this fluid ingress, but it can only account for a very small proportion of rare earth mineralization, because as we discussed earlier on in the talk, the rare earth contents in calcite and to a lesser extent apatite are very small compared to those which are partitioning into our alkali rare earth carbonates. And I just want to mention here, before I move on, this process of dissolution of previous minerals formed from a melt, such as calcite and apatite, releasing rare earths, during a hydrothermal event very much blurs the line into weathering processes, which I'll talk about in just a moment. So just to schematically revisit everything I've just said, we have a nice cartoon diagram of this again. We have our evolving now from bottom to top, our evolving carbonatite system going into a brine melt. And now this brine melt has been replaced by an influx in bright blue here of a hydrothermal fluid after some sort of brecciation event. And this fluid back reacts with our host carbonatite, breaks down our host bourbonkite. So these would have all been bourbonkite minerals over here, and replaces them with an assemblage of a rarer fluorocarbonate, in this case, bastnasite, BSN, bastnasite, barite, and strontianite. And we also have partial dissolution of minerals such as apatite, where our rare earth rich apatite in pink is replaced by a rare earth poor apatite in green and little monozyte grains. And also our host carbonates start to get broken down, and you have little replacement carbonate phases coming out of them as well. So this is what our normal rare earth ore deposit looks like. It looks like something which is probably formed from a bourbonkite rich dolomite carbonatite, and then has had hydrothermal fluid ingressing and replacing those bourbonkite grains with a rare earth mineral. And this can either be good in the sense that you can perhaps replace it with something like monozyte, which is relatively easy to process, or it can actually be disadvantageous. We're not adding any more rare earths to our mix here. And what can happen instead is that we form an assemblage of very fine grain intergrown rare earth fluorocarbonates or other phases which are more challenging to extract from a mineral processing point of view. You can also have some recrystallization of calcite and apatite. This can increase the grade of your rare earth extractable minerals, but on the other hand, it makes the deposit really gunky. As a byproduct of this, you get lots of things like iron oxides and secondary carbonate and oxide minerals, which can make, again, the deposit difficult to process. So the last step to make our rare earth rich carbonatite is weathering. And like I said, this blurs the line from a hydrothermal system to a weathering system. But what we have in a weathering environment that's advantageous is essentially a carbonatite sitting at the surface and surface waters leaking through, reacting with the carbonate minerals, dissolving them and stripping away the calcium and the carbonate. And this removes the carbonate part from our carbonatite deposit. And in doing so, residually increases the grade of our rare earth deposit by however much carbonate is lost. So in the case here, this is the Ngwala deposit in Tanzania, where we have a fresh carbonatite with 1.5 to 2% rare earth oxides. You know, that's fairly decent actually, but in the weathered zone, we have 140 meters on top of that, which is from 3 to 8% rare earth oxides. It's a much higher grade deposit because we've removed all of our carbonate minerals and residually increased our rare earth contents. This is like the seasoning to a good rare earth deposit. But it's not always good, because in this process of dissolution of the carbonates, we can also partially dissolve some of our rare earth minerals as well and reform them. And as they reform, they react with the surrounding phases, and you can get minerals from the trandolite group, which form small, gunky, fibrous, difficult to extract rare earth phases, and also hydrated rare earth phases such as rhabdophane, which is the hydrated equivalent of monozyte. We also form extensive secondary iron oxides, the phases like goethite, and all of these things make extraction of our carbonatite much more challenging, of rare earths from a carbonatite much more challenging. So that's it from me. These are the 5 ingredients. I've gone through them step by step. We need to metasomatize our mantle, get that melt to the surface. If it's immiscible, we need to separate it from our silicate rock at a relatively late stage. We then need to fractionate away all the stuff which isn't rare earths and suppress silicon while we're doing so the rare earths don't go into apatite. We form a brine melt from the residual sodium, potassium, and volatile phases, and this leads to bourbonkite crystallization. This makes nice bourbonkite-rich pegmatites or dolomite carbonatites, which are then brecciated and recrystallized and form light rare earth fluorocarbonates or monozyte. And we can also have some dissolution of calcite and apatite from previous stages, forming rare earth minerals as well. And then lastly, if we weather it, we can strip away as much carbonate as possible and just leave the rare earths. So if we hit all of these things, ideally, we have the perfect carbonatite deposit. No single deposit meets all these criteria, but many meet some of them. And I'll just end up by thanking the various co-authors, so Michael and Wei, who co-wrote this review, but also industry collaborators from predominantly Mekango Resources and eTech, Delia, who's a PhD student of ICOSO, provides at Leeds, and also the crew from Camborne, Francis and Pete especially. And end with a nice picture. Thank you very much.